In this video, I introduced the definition of a matrix and define the main arithmetic operations on it. So first, all a matrix is a rectangular array that contains numbers called entries or elements. The size of a matrix is given by the number of rows of that matrix by the number of columns. We normally say this by m by n. So for example, this matrix here is a 3 by 2. It has 3 rows, 2 columns. Now there are special types of matrices. One is the m by 1 matrix. It essentially has only one column. It's called a column matrix, and we often also just call it a column vector. A 1 by n matrix is a matrix that has only one row. It's called a row matrix, but we often just call it a row vector. So if you're given some kind of matrix, we can also refer to the columns and the rows by labeling them. So we'll have a common convention to do so. If you're given this one matrix, the ith column of a matrix is written usually in boldface on the text. We write with vectors sometimes if you write it down on a page. And we'll use lowercase letters to describe the columns of that matrix. So if the matrix is called A, lowercase a with a subscript refers to the first or second column. If though you use the capital letter in boldface and use a subscript, that's referring to a row. So for example, for the matrix A, capital A sub 1, capital A in boldface, that refers to the first row. Now there's many ways to write down matrices, many ways. But it's common that you only care about when you're talking about quickly, that you might want to mention for whatever reason, what are the names of the elements. So then if you want to do that, you could write down the matrix A, put brackets around lowercase a, and then refer to the entries as ij. So when you write ij, it's understood that you're talking about the ith row and the jth column, as long as both the number of rows and columns in the matrix is 9 or less. So it's not confusing, because if you have 10 rows or 10 columns, because of the extra digits, you're not sure which digit goes for the rows and columns. So if it's in any way confusing, we'll put commas between the I and the J. Also, sometimes we refer to the matrix, its ith, jth entry, by going and using the capital letter. All three of these are interchangeably used. If though you want to talk about the matrix all at once, but generally just give you a physical feeling for it, you write down this way. So here you're writing down the various entries of the matrix, but you're leaving out many of them because you don't know the actual size of the matrix. So notice the very last row, all the entries start with m. That's the mth row, and then first column, second column, third column, so on. And the very last column, the very last entry in that subscript is an n, because that's the nth column. Notice there's a lot of ellipses in order to tell you the pattern continues. You can also, which is convenient, describe the matrix as a matrix of column vectors. Or you can describe the matrix as a matrix of row vectors. That way you emphasize those things. There are many special types of matrices. So I'm going to give you a definition of a bunch of them now. Given a matrix A whose entries are A sub ij, that is m by n, the diagonal entries are A sub 1, 1, A sub 2, 2, A sub 3, 3. It's essentially all the entries along the matrix where the row index and the column index are the same. Notice that I'm not assuming here that the rows and columns of the matrix are the same. They don't have to be. So essentially all matrices have diagonal entries. Now, if you have a matrix where all the entries are 0, again, it doesn't matter what the size is, that's called a 0 matrix. But that means there's also an infinite number of 0 matrices, so you can't say the 0 matrix, it's just one of them. A matrix is called square if the number of rows equals the number of columns. Any square matrix whose non-diagonal entries are 0, that's called a diagonal matrix. Any diagonal matrix whose diagonal entries are all equal is called a scalar matrix. And if in addition, if you have a scalar matrix and all those diagonal entries are not only equal, but they're equal to 1, that's called an identity matrix. Now, just so you're sure, an identity matrix being square the number of rows equals the number of columns, but I don't know how many there are. So there's actually many identity matrix. There's a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, and they're all not the same. So obviously what we need then is some kind of definition for what it means for two matrices to be the same. We're going to use the same definition we use for vectors. Two matrices are equal if and only if they have the same size, and all corresponding entries are equal. This is a good time then to go and look at some examples. Here is an example of a zero matrix. All the entries are zero. Here's just some square matrix. And if you want to know the main diagonal, these are the main diagonal entries. All the entries whose row and column index are the same. This is a diagonal matrix because everything off the main diagonal, all those non-diagonal entries, are zero. This is a scalar matrix because it's diagonal, but all the entries on the diagonal are also equal, and that is one diagonal matrix. It's the only 3 by 3 identity matrix. There's only one. But there are other identity matrices because they could be 2 by 2, 4 by 5, 5 by 5, 6 by 6, even 1 by 1. Now, if you have two matrices being equal, such as these two matrices here, that's possible because these two matrices have the exact same dimensions. They both have the same number of rows and columns. So the two matrices have identical rows and identical number of columns. And if those two matrices are equal, then that means then that A has to equal 1 and C has to equal 3 and vice versa. Because if they're equal, then corresponding entries must be equal also. Lastly, because it's confusing, up to this point we've been using row vectors, column vectors kind of interchangeably. That's because we're thinking of them as vectors. If we ever want to think of them as specifically as matrices, then they're not equal. These two things are not the same, even because they're not the same size. The matrix on the left is a 1 by 2. The matrix on the right is a 2 by 1. So those are not considered equal when you think of them as matrices. If you want to think of them as representations of vectors, yes, now they actually are equal. So the context matters in the problem. And now that we've defined a matrix and we've given names to matrices with special properties, let's now talk about the operations on those matrices. For example, matrix addition, matrix subtraction, multiplication of a matrix by a scalar, and then the product of two matrices. So in some cases, we're just going to steal from vectors. So we'll say then that if you give me two matrices of the exact same size, their sum is found by just adding the corresponding entries, and the result is a matrix of the exact same size. If, though, the two matrices are different size, then you cannot add them. For example, these two matrices in my example here are the same size. They're both 2 by 2s, so you can add them. You just add their corresponding entries, get a 2 by 2 matrix. On the other hand, these two matrices we cannot add. It doesn't mean anything because they're different sizes. They have a different number of columns. So that addition doesn't mean anything. Similarly, we'll just steal from vector scalar multiplication to define matrix scalar multiplication. So if you give me some matrix and some scalar, the scalar multiple, the scalar times the matrix, is defined to be a matrix of the exact same size as the original matrix, but where you just multiply every single entry of A by that scalar. So for example, if you take that matrix 2 times the matrix 2, 3, 5, 3, the matrix will be a 2 by 2, and all you do is just multiply all the entries. And it's pretty simple. Lastly, if you go and want to know how to do the subtraction of two matrices, by using the property of matrix addition and matrix scalar multiplication, you can see subtraction as a very natural way as just adding the opposite of a matrix. In the end, that boils down to just subtracting corresponding entries, provided that the matrices in that subtraction are the same size. If the matrices are a different size, you can't subtract them. Now, the next one is fairly interesting. We have to lead into matrix product. To do a matrix product, we want to connect it with ideas we've already developed. In this case, linear combinations, as it's the main driving force in almost everything we do. So if you give me a matrix that is m by n and a column matrix that is a n by 1, that matrix is B, then we write the product of the matrix A by the column matrix B as A times B, and it equals a linear combination of the columns of A, but using the entries of B as the scalars. So I wrote down a notation here for you, and I'll give an example to show you what I mean. So I want to know, what is this product? Now to check it, if you look at the definition, it requires the matrix to be m by n and the column matrix to be an n by 1. That's not a mistake. That means the number of columns of A has got to equal the number of rows of B if you want any chance of doing the multiplication. If they're not equal, you simply can't do that multiplication. This would then be a linear combination of the first and second columns of A, but using the entries of B as the scalars, and the order lines up. So then that would be that linear combination, which is the vector 22, 0. So the matrix product of this matrix A times this matrix B is the column vector 22, 0. From there, you can define general matrix multiplication. So if you give me a matrix A that is m by n and a matrix B that is n by r, notice this is not by mistake. The number of columns of A has got to equal the number of rows of B, or the multiplication is not defined. Focus in on the column vectors of B, B1, B2 up to BR. The product of these two matrices, A times B, is a m by r matrix whose ith column is the product of the matrix A to the ith column of B. So A times B, notationally, you think of it as A times a matrix with column vectors, and you can kind of distribute the A through. So this is really nice algebraically, also conceptually, because it expresses things in terms of linear combinations. It's really, really nice. Quickly, it says then that the matrix product of A times B forms a matrix whose columns are linear combinations of the columns of A. It's really important for later on to notice that. This particular form of matrix multiplication is called the matrix column form. Alright, so now that definition is strange enough, especially if you've seen matrix products before, because then you would have been taught a simple version that doesn't really help us for linear algebra. We'll get to that one later on. I'm going to show you an example of multiplying two matrices. So we're going to multiply these two matrices. I'll call them naturally matrix A, matrix B, and the product will be called matrix C, so that I can refer to the matrices instead of left and right matrix and first and second matrix. Notice that these two matrices, the matrix A has two columns, the matrix B has two rows, so because of that, the product is defined, and the product is a 3 by 2. It's the outer numbers. So then that 3 by 2 has two columns. Let's find the first column of C, the product of A and B. So the first column of C is found by taking the matrix A and multiplying it by the first column of B. That is a linear combination of the columns of A using the entries of that first column of B as the coefficients. So then C1 is that linear combination, and that's 1, 3, 0. That's the first column of this product. That's the first column in C. For the same thing, I can find the second column in C, the second column in the product, by taking the matrix A and multiplying it to the second column of B. That again is a linear combination of the columns of A with the entries of this column vector as the coefficients in that particular linear combination. So the second column of C, the second column in the product, is this 3 by 1 column matrix, 1, 8, negative 1. Putting this together, that's the product. Nice, right? It's simple. But if you look at these two matrices, the same two matrices, but now reverse their order, not only does it not equal the original product, but now it's not even defined. Not even defined. That's because the inner numbers here are not the same. The number of columns of the first matrix does not equal the number of rows in the second matrix in that product. So that product is undefined. That's very disturbing because this is the very first time that you've been introduced to some kind of a multiplication between objects where the order really matters. In this case, the order matters so much that in one order, the multiplication not even defined. Now that we have the basic definition of matrix multiplication out of the way, there's many ways to do that matrix multiplication. I gave you what was called the matrix column form. The point of it is to show you that the product of two matrices is actually defined so that the columns of the products are linear combinations of columns of the first matrix in that product. It directly connects matrix multiplication to linear combinations. But many students, when you're first taught how to do matrix multiplication, you're not taught that, which is unfortunate because then you have no idea why you're doing the multiplication the way you are. You're just told to do it. So, but the other versions is easier to follow and also has other benefits. So there's three other major forms. There's the row matrix form, there's the row column form, and then there's the column row form. Out of the three, the row column is the one you see by far the most. The remaining two I'll go over, and I'll do it in decreasing order of importance, or at least in terms of what you'll actually see. There are other ways to do matrix multiplication besides that too, by using what's called matrix partitioning, but they all boil down to the same idea. The remaining results here all give the same product. That's why they're in red boxes, because they're theorems. I'm just choosing not to prove the result. So, given a matrix A, which is m by n, and a matrix B, that is n by r, their product will equal a m by r matrix whose ith jth entry equals the dot product of the ith row of A when thought as a vector and the jth column of B when thought as a vector. This is called the row column form. It is by far the most commonly used just because it's really simple. So as an example, let's look at the product of the two matrices A, B, and I'll call that matrix C so I can refer to it. I want to know what is the second row, first column of C, the product of A and B. To do that, just find the second row of A, think of it as a vector. Look at the second column of B, think of it as a vector. Read the vector's entries from left to right or top and down and just do their dot product. So that entry is 5. So the second row, second column entry of C, the product of A and B, is going to be the entry 5. If you want to know the first row, third column of C, that's the first row, third column of the product AB, take the first row of A, take the third column of B, read left to right, top down, and just do the dot product like they're vectors. That number's 4. Quickly, you can probably see how this will be done. I want to know the first row, first column of the product. So you would take the first row of A, take the first column of B, treat them as vectors, read left, right, top, down, and take their dot product. This method allows you to pinpoint. You can then find one entry. You don't need to find the entire matrix. You can find one entry of that matrix. So by doing so, you can see that this then is the product. I'm just not going to do the remaining 3 entries. So as a quick drill, see if you can do it. So if I give you the matrix A and the matrix B, I want to know the second row, first column of their product. So if you can see it, I would then focus in on the second row of A, which is right here. I would take the first column of B, that's right here, and then I would just do the dot product, reading left to right and top down. So that would be 1 times 2 plus 4 times 3. That entry winds up being 14. So the entry in the product would be in the second row, first column. That number's 14. You also know, by the way, what the resulting product has to be, because the first matrix A is a 2 by 2, the second matrix B is a 2 by 2, so the product is a 2 by 2. So there's 3 more entries for me to worry about. But you know, I don't care about that for now. The next thing would then be is, can you just see that it's defined or not? So if A is a 2 by 3 and B is a 3 by 7, is A times B defined? Yeah, because the number of columns of A, 3, equals the number of rows of B, 3. So that matrix A times B is defined. And it's defined to be the outer numbers 2 by 7. So AB has 14 entries in them. You have to use probably this technique, the row column technique, to find all of them. Notice though, if I reverse the order and ask, is B times A defined? No, it's not. Because the number of columns of B does not equal the number of rows of A. So B times A not only doesn't not equal A times B, it's not even defined. So it's really natural to ask that if the product of two matrices gives you a matrix whose columns are linear combinations of the columns of the first matrix in that product, when you multiply two matrices, would the result be a matrix whose rows are linear combinations of the rows of the second matrix? And yeah, and this is not terribly useful in terms of actually doing the matrix product, because we already have two ways to do that. We don't need yet a third. But it's important, though, to notice that it is true for arguments later on. Because if you remember, there are certain operations that we can do on matrices that forms linear combinations of the rows. So, just to lead you into it, if you have a 1 by n row matrix and an n by r matrix B, notice the number of columns of A equals the number of rows of B. The matrix product A times B is just a linear combination of the rows of B using these scalars or entries of A as the coefficients. And I just wrote down notation to show you what it means. As an example, if I wanted to do that particular matrix multiplication, a row vector to a matrix, that matrix is defined. It's a 1 by 2 times a 2 by 2. So that's a 1 by 2. So it will be a row matrix. That is a linear combination of the rows of the second matrix, with the coefficients being the entries of the row vector. So that multiplication has to be then 11, 0. Now once you have this, it's natural to go from this point to go into general matrix multiplication. This is called the row matrix form. So if you're given an m by n matrix A with rows A1, A2 up to AM, and a n by r matrix B, their product will equal a n by r matrix whose ith row equals the ith row of A times B. And again, I wrote it out notationally. So it kind of says that you can kind of distribute B from the right into a matrix of row vectors. And that will actually be notationally, that's notationally the right way to write down the resulting product. So that's kind of cool that that's true. I think, though, that you should remember that the ith row of AB is therefore a linear combination of the rows of B, and whose coefficients are the entries of the ith row of A. So the product then is a bunch of row vectors that are all linear combinations of the rows of B. As an example, let's go back to the original two matrices I did when I multiplied these two things together, when I used the matrix column form. So this multiplication is clearly defined because the number of columns of the first matrix equals the number of rows of the second. So using the row matrix form, I'd like to know what is the first row of their product. So I take the first row of the first matrix and I multiply it to the second matrix, and I think of it as a linear combination of the rows of the second matrix. The coefficients used in that particular linear combination are just the entries of the row vector. So then you get the vector 1, 1. I want to know then what is the second row of the product. So take this second row of A and just multiply it to B. That will then be a row vector times a matrix. You can see that as a linear combination of the rows of the matrix using the scalars in that row vector. I wrote it down. That should be 3, 8. And the last one, I want to know the third row of their products. So take the third row of A and multiply it to the matrix B. That'll be a row vector times a matrix. So that would then be, it's a linear combination of the rows of the matrix B where you use the coefficients found in the entries of A. And I wrote it down. So if you just multiply out these matrices, you get what we got before. Notice that it doesn't matter. You can do any of the three techniques I just gave you in order to find the product of two matrices. This last one really is just here to mention to you that notice that matrix multiplication forms linear combinations of the rows of that second matrix. So all of the rows of the products are linear combinations of the rows of the second matrix. So if you have learned anything about the way we've defined matrix multiplication, it's that this theorem is true. That if you give me any two matrices so that their product actually is defined, then the columns of the product are just linear combinations of the columns of the first matrix in the product. And the rows of the product are just linear combinations of the rows of the second matrix in that product. How to actually do the multiplication, we almost actually use the row column form by doing it element by element. But this is a very nice thing to remember because this is why matrix multiplication is so strange, because we want this to be true. Now, as a simple example of using it, let's suppose that A is any matrix and let E sub I be a row vector. That's a standard vector, so that means that all the entries are 0 in this case except for the ith entry. And EJ be a column standard vector. In this case, it's standard means that all the entries are going to be 0 except for the jth entry. Then if you take EI times A, that's actually the ith row of A. And if you take A times EJ, it winds up being the jth column of A. Why that's true is easy. I gave you an algebraic proof here. If you take A times EI, it's just a linear combination of the columns of A, but the scalars in that combination are all 0 except for the ith entry, and that's 1. So it's 1 times AI, which is the ith column of A. And that's the proof. The other for part A just uses the row matrix form of multiplication to show why it's true. Now, there are as I said, 4 common multiplication you see, but really they go down in terms of frequency until the very last one is almost never seen or used. It's called the column row multiplication. It's called the outer product expansion, if you ever want to hear it somewhere else. In this case, you take A and you break it into columns. You take B and you break it into rows, and you think of the multiplication as a row vector 1 by n whose entries are not numbers but are column vectors, and the second matrix you think of it as a n by 1 row vector or n by 1 column vector, but where the entries are row vectors, and then you just do the multiplication like you always would. In this case, you wind up getting the correct answer. It's the same thing. It winds up being a sum of product of matrices. Now again, this is not something you usually use to actually go do any kind of multiplication. It's there to show that it can be done, that a product of two matrices can be written as a particular sum of products of particular matrices. But I think, though, it's a good idea to actually see it with numbers at least once. So I want to know what is the product of these two matrices. I'll call them A and B, and we get the matrix C as the answer. So notice the columns of A is equal to the number of rows of B. We've done this multiplication before, so we know what the answer should be, but I'll use the outer expansion. So then that would be this particular sum of products. Now in the first product in that sum, I have the column vector 1, 3, 0 multiplied by the row vector 1, 2. I can think of that as a matrix times another matrix, and I can use that idea to go about finding out what would be then that product. The actual product it's a matrix that is 3 by 2, but whose all columns are just multiples of the vector 1, 3, 0. And the multiples are the scalars you see in the second vector. So then that's the actual product. The second product in that outer expansion is the column vector 1, negative 2, 1 times a row vector. That will then be a 3 by 2 matrix, and the result will be a bunch of columns, where the columns would then be multiples of the matrix 1, negative 2, 1, and the scalars are found in the second matrix in that product. That would then be this, 0 times the first vector, and negative 1 times that vector, 1, negative 2, 1. Then if you add those together, you get the answer. And that's the exact same answer we got before. Again, this is not one of those things that's really super terribly useful, but it's nice to know that you can write the product as a sum of products of particular vectors, where those vectors are columns of the first matrix or rows of the second. So one last way to look at multiplication between matrices. Again, this is not terribly useful at the level you're at, but as we move along in the course, it eventually will become useful here and there. So it's nice to see it. All of these forms of matrix multiplication after the very first one, after matrix column form, are all forms of what we call partitioning a matrix comfortably for matrix multiplication. When you partition a matrix, you're just breaking it up into submatrices. How you do it is you use lines. You make a bunch of horizontal lines, a bunch of vertical lines, and it breaks it into a bunch of submatrices. So when you take a matrix and think of it as a bunch of column vectors, that's actually a column partition. If you take a matrix and you break it into all of its rows, that's just the row partition. We say that matrices are set up are comfortably partitioned for block multiplication if, when you break up the matrices into different submatrices, that the partition of the matrix on the left is such that the columns in that partitions equal the rows in the second partition for the second matrix. For example, here, I could see that these two matrices, as you multiply them together, would be a 3 by 3. I could do that lots of ways, but I'm going to choose to do it this way. The reason is, notice by breaking the matrix up this way, do you see how a bunch of the submatrices are zero matrices? Now, anything times a zero matrix, as long as it's defined, is going to be a zero matrix. So that makes it really easy to add to other things. Okay, so then this would then be comfortably partitioned for block multiplication. Because in the first matrix, notice the columns, there's 2 in this one, there's 1 here. And for the rows, for the second matrix, there's 2 here and 1 there. So then the columns of the first partitioned is equal to the rows of the second partitioned. It's the numbers that line up. The other part of the partition doesn't matter. So where we put the horizontal line in the first matrix doesn't matter. Where we put the vertical line in the second matrix doesn't matter. Okay, so this is comfortably set up. Comfortably set up. So think of it as it's a 2 by 2 times a 2 by 2. So there's a 2 matrices, there's a 2 by entries, there's 1 here, there's 1 there, there's 1 here, there's 1 there. So it's a 2 by 2 times there's 1 here, there's 1 here, there's 1 here, there's 1 here. It's a 2 by 2. So it's a 2 by 2 of matrices times a 2 by 2 of matrices. The answer should be a 2 by 2 of matrices. And there you go. I made a 2 by 2 matrices. You can see the dotted lines. I just want to know then, what is then that submatrix? To do so, it's literally just like matrix multiplication, just line up things correctly. So look at the second row of the first matrix, take the first column of submatrices in the second matrix and multiply them, reading left to right, top and down. Always keep the order of the product the same. So I always have the submatrices from the first matrix first. That would then give you this. Now just multiply that like you always would. But if you multiply all that out, you're going to get the vector 0, 0. So then that's the answer. That goes in that entry right there. So that means then it's actually pretty easy to multiply matrices if they have certain special forms, because we can use this block multiplication trick to usually pick out a whole lot of zeros. It's not really useful for anything else though, but it's really useful for that though. Now that we have general multiplication of matrices down and we thought about various different ways, you'll use by far, most students just rely upon the row column form to get all the multiplications. Just remember though that the reason multiplication is defined the way it is to get it connected to linear combinations in some way. The outer product is nice, but you really won't see it very often. And partitioning a matrices to make it be comfortably partition for matrix multiplication is also another one of those you'll almost never use it, but it's something you really should know about as it can help to find multiplications. So, for example, what if I wanted to go about finding out the product of these two special matrices? Now notice these matrices are diagonal matrices, so I want to know what the entry should be. Now you would hope that the product of two diagonal matrices is diagonal, and in fact that's true. In fact, I can give you the answer really quickly about how to actually get the answer in the end, and we don't have to do normal multiplication, but we'll have to do it once. So the product of these two matrices can be thought as the multiplication of the matrix A with the multiplication of, think of it like a row vector whose entries are columns, and the columns are 2 times E1, 5 times E2, and negative E3. But then when you look at it that way, that multiplication is in matrix column form, and I literally just multiply the eighth row. And then the scalars, scalar multiplication can be put anywhere, so I'll just put the scalars out front of those particular columns. But then A times E1, we did that multiplication already. That is the first column of A. And A times E2, that's the second column of A. And A times E3, that's the third column of A. So you get this. But then we know what those columns are, so I can just do the multiplication. That's 2 times the first column, 5 times the second, and negative 1 times the third. But then if you look at it one last time, notice that you're only actually multiplying these scalars to certain entries in those vectors because there's only certain ones that are non-zero. That's the same as this. So it winds up being that the product of two diagonal matrices is a diagonal matrix. And the entries on the main diagonal of the product is the product of the entries on the main diagonal of the factors in that product. You literally just multiply corresponding entries. This is the only time. This is the only time when you can multiply two matrices by multiplying corresponding entries. Anything else, it doesn't work. Anything else, it doesn't work. But for diagonal matrices, it does. So that's nice. So as an example, if I wanted to multiply a matrix, a diagonal matrix to itself, that would just be found by literally multiplying the diagonal entries to itself. That'd be 1 squared, 2 squared, and that would then be 1, 4. There's something else about that product, though. It's the matrix 1, 0, 0, 2 multiplied to itself. I'd like to have a faster way to write that. So we define exponents. So if A is a square matrix, then A to the n is understood to be a matrix just multiplied to itself, where it's found in the product n times. And A to the 0 is understood to mean the identity matrix. Now, why would that be true? Yeah, it's something that we need in general for later on. So A to the 0, if that's defined, which you won't understand for a little bit, if A to the 0 is defined, then that's understood to be the identity matrix. Notice that this is only true for a square matrix, because if it's not a square matrix and you multiply a matrix to itself, well, then the columns and the rows won't line up. You can't do the multiplication at all. So if I wanted to do this particular square, it literally just means take this matrix 2, 0, 1, 4, and you multiply it to itself 2, 0, 1, 4, and then you just multiply it out. So this would then be a 2 by 2. And the first entry would be 2 times 2 plus 0 times 1. That'd be a 4. First row, first column. Then I'll do first row, second column. It'd be 2 times 0 times 4. That'd be 0. Then you have second row, first column. That'd be 1 times 2 times 4 times 1. That'd be 6. Then you have second row, second column. That'd be 1 times 0 plus 4 times 4. That'd be 16. And that's the answer. That would then be the product of that. Notice, by the way, that in this case, I wound up squaring the entries on the main diagonal, didn't I? But I did not square the entries, all of the entries on the off diagonal, the non-diagonal entries. So you can't just distribute powers. That's unfortunate. You can't just distribute powers. But you can distribute powers if the matrix was diagonal. The last operation. So matrix transpose is a way to take a matrix and sort of flip it around its main diagonal. Literally, all you do is interchange rows for columns and columns for rows. So the ith column of A transpose is the ith row of A, and vice versa. In notation, the ith jth entry of A transpose is the j'th entry of A. If you have a square matrix, then it's possible that the transpose equals itself. Because if it's not square, then the transpose cannot equal the original matrix because they're different dimensions. So if a matrix is square and the transpose is equal to itself, we call it symmetric and vice versa. For example, here's a matrix and I took its transpose. Notice everything on the main diagonal stays where it is, everything else flips around it. And that's it. This matrix is not symmetric because the transpose of it is not the original matrix. And that gives you the basic definition of what a matrix is, their addition, their subtraction, their scalar multiplication, and then all the ways to get the matrix product, and the reason that the matrix product is defined in such a strange way. After that, I went into exponents of matrices and the transpose. I also emphasized that the product of a matrix times one of those standard vectors winds up being a row or a column, depending upon the order of the multiplication.